Okay, so in lesson 9, we're going to focus on a section called radicals and conjugates. In other words, we're going to basically take square roots and we're going to introduce cube roots, and we're just going to simplify them. So you've probably done this in Algebra 1, a little bit in geometry. We're going to rehash some of these ideas here. We're going to skip the opening exercise. I'm going to start with example number 1, where it says express in simplest radical form and combine like terms. So in other words, they want us to pull as much of the perfect square stuff out of these radicals as we can. If we get like terms, combine them. If not, leave them alone. So, for example, if we were to look at the square root of 50, let's just look at that one. I can think of a perfect square that goes into that, and that would be 25. So I could rewrite 50 as 25 times 2. Now, is that the only thing that gives you 50? No, you could think of 5 and 10 and 1 and 50. But the reason why I'm choosing 25 and 2 is 25 is a perfect square. Well, how do I know that? Because I know that 5 squared is 25. That makes 25 a perfect square because I was able to square the 5. So if 25 is a perfect square, I can pull a 5 to the outside and leave a 2 on the inside. So we'll do the same idea again, but this time we're going to do it with the 18. So we'll put the minus sign. We're going to take two things that multiply to equal 18. The requirement is one of them has to be a perfect square. So that correct choice would be a 9 and a 2. So the square root of 9 is 3. So we put minus 3 with a radical of 2, square root of 2. So now we do the same thing with the 8, right? Something that multiplies to equal 8 such that one of the factors is a perfect square. So that would be 4 times 2. And so in this case, the 4 is the perfect square, so the square root of 4 is a 2, so we bring a 2 on the outside, and we have a radical 2 on the inside. Now, again, in this particular case, we are fortunate. All the radicals are alike. For example, here's what I mean by that. If we were to combine like terms, let's say I had 5x minus 3x plus 2x. We would say those are all like terms. And so I'd be able to do 5 minus 3, and that would give me 2. And I would add 2, and I would get 4x. Well, radicals work the same way. If all the radicands, this part right here, are the same, I can combine like terms. So 5 minus 3 would be 2. I add 2, I get 4. So my final answer is 4, but the radical stays the same. It is treated similarly to the variable design in that perspective. So again, what we're going to see in the next several exercises, and I'm going to work out each one, is several different scenarios that could occur as you choose to simplify radicals in this lesson. So let's look at exercise number 1. It says the square root of 1/4 plus the square root of 9/4 minus the square root of 45. So they're going to want us to simplify, and if we have any like terms, combine. So if I looked at each one, for example, if I looked at the first one, right, square root of 1/4, I could rewrite this. Now you could just do this step, but I'm going to show. You can rewrite this as the square root of 1 over the square root of 4, and then I could write plus the square root of 9 over the square root of 4 and I could put minus, and we'll deal with the 45 in a little while. Now, the reason why I separated this is doing 1 divided by 4 first would give you 0.25. And the only way you're going to take the square root of that is to pick up a calculator, and that is our goal not to do. Our goal is to simplify, not get a decimal answer. But if I was to take these fractions and put a radical in the numerator and a radical in the denominator, it turns out the 1, the 9, the 4 are all perfect squares. So the square root of 1 is 1. Square root of 4 is 1/2. Square root of 9 is 3, and the square root of 4 is 2. So now I bring down my minus, where is that? There we go. Minus square root of 45, and again we'll deal with that in a minute. Now if I do 1/2 plus 3/2, or basically 0.5 plus 1.5, then I'm going to get 2. Now for the 45. If I can think of a perfect square, it goes into 45, I can simplify it. So I'm going to replace that 45 with a 9 times a 5. The square root of 9 is 3. So out comes a 3. So 2 minus 3 radical 5. They do not both have radical 5s. Since they both do not have radical 5s, we cannot combine any like terms with this particular piece. So that ends up being the final answer for number 1. So number 2, different scenario, right? Just like distributive property. So in this case, if I was to distribute, I can multiply what's inside a radical with another one, and they do not have to be alike. So I could say square root of 2 times the square root of 3, and I'm going to get the square root of 6. And then I can do the same thing here. I can multiply these two, and I get minus square root of 4. And then we'll see if there's anything that can simplify. Well, there are no perfect squares that go into 6, but this one is a perfect square, so I can write the square roots of 6, and then I could say minus 2. So that would be our final answer. There's nothing else I can do with that. For those of you who don't like to have a number behind the radical because you can't tell if the line is supposed to go all the way or not, then that's fine. We would put, yeah, right here. So let's see, we could put the negative 2 in the front. And then you could put the square root of 6 in the back. So either one. So you could, both of these are acceptable answers. You do not have to do the second part right here at the bottom. I like to do that because I like to keep my number in the front, my radical in the back, but that's just a purely personal opinion on that design. So let's say we look at number 3. Right, we're at the square root of 3 over 8. Well, 3 over 8 would give us a decimal. It's not going to help us. So we're going to apply the same kind of strategy we did before. I'm going to put the square roots of 3 here, and I'm going to put the square root of 8 here. Now we have to think strategy about what we want to do. We know that ideally, if this was a 16, we could have a perfect square because the square root of 16 is a 4. So what I am going to choose to do is I am going to multiply by the square root of 2 on both the top and the bottom. So when I do that, on the top, I'm going to get the square root of 6. On the bottom, I'm going to get the square root of 16. Now, by doing that, the square root of 16 is now a perfect square. And so my final answer is the square root of 6 over 4. Now, we did that process because we wanted to avoid having a radical in the denominator. There are other ways that we can do that, but this ended up being just one strategy that was very efficient to make that work. So let's look at number 4. Number 4 is different. This is a cube root. Now, if you're not sure what a cube root is, for conversation, that's like saying 2 times 2 times 2. That would be 2 to the third power, and that would be 8. Likewise, if I said 3 to the third power, that would be 27. Here are some of the common ones. 4 to the third is 64. And 5 to the third is 125. So again, we're going to apply the same kind of strategy we just did, right? We're going to rewrite this so it says the cube root of 5 over the cube root of 32. Now, 32 is not on my list. But if you observe and you strategize a little bit, you think, well, it would be really nice if I had the 64. And so it turns out, if I were to multiply the top and bottom by the cube root of 2, right? Making a conscious choice because I am making the problem do what I need it to do to be nice. I can choose any number I want here, as long as I do it to both the numerator and the denominator. And again, why am I choosing a 2, say, versus a 3 or a 4 or something else, is I want to get this 64. This 64 would be nice to have. So when I do this, because they're all under the radical, I get the cube root of 10. And when I multiply these, I get the cube root of 64. Now that 64 is on my perfect cubes list. So by doing that, the numerator is going to remain the cube root of 10. There's nothing I could do about that. But the cube root of 64 is 4. So that allowed me to simplify that particular piece. Let's say number 5, another cube root. Right? So in this case, there's no fraction here, so our strategy changes a little bit. And what you might notice is we see a variable come into play. So if I'm going to try and do this, I'm going to write the cube root. And remember my perfect cubes, right? Some of them were 8, 27, 64, 125. They keep going. These are the most common 4 that we're going to see. If I don't like that 16, I can replace that 16. I know something else that multiplies 16. That would be 8 times 2. 8 is a perfect cube. 2 is not. 2 is going to be remaining inside that radicand. Now for the 5, right? I'm going to break that 5 up into an x to the third power times an x squared. If you recall exponent properties, bases with equal bases with radical with exponents you add together. So 3 plus 2 is 5. Every time I can create an x to the third power under here, I can take an x out. So we'll demonstrate that. So now we're going to take the perfect cubes. The cube root of 8 is 2. So that comes out. So that one's done. The 2 here is going to stay behind. X to the third, this 3 matches this 3, so I get to take an x out. This one is less than 3. I cannot create a 3 with that. So left over in the radical will be my 2. This is a cube root, so we want to put a little 3 there. And then an x squared. That's going to be our final answer. Again, the cube roots, they take a little bit more practice. I, of course, would encourage you to ask me questions as you go through the practice set and you discover some that you want to learn about, and so forth. All right, so we're almost to the end of the lesson. We got a few more to look at, though. So what about this right here, multiply and combine like terms? Then explain what you noticed about the two different results. So when we multiply these together, in example number 2, right, notice these. This says this one and this one are the same. This one's got a plus sign, this one's got a minus sign. What you're going to do is we're going to discover something that's going to happen. So we're going to do the distributive property. So radical 3 times radical 3, that's going to be the square root of 9. Right? If you see that that's going to be a 3, you could just write a 3, but I'm going to save that for another step. This becomes the square root of 6. If we multiply here, this becomes another square root of 6. And this one is going to become square root of 4. So now we're going to attempt to simplify. Right? So the square root of 9 is 3. We've got square root of 6 plus square root of 6. Those are like terms. So that'll become 2 square roots of 6. Remember, the number in here will not change when you add. Square root of 4 is 2. So the last two like terms I got is this constant of a 3 and this constant of a 2. And so we get 5 plus 2 square roots of 6. That'll be the final answer for that one. Now let's compare what's going to happen with the other one. Right? If I multiply radical 3 times radical 3, we'll get square roots of 9. Again, you could just put a 3 if you like. This one is going to become a negative square roots of 6. This one will be a positive square roots of 6. And this will become a negative square roots of 4. So now when we combine, square root of 9 is 3. Negative 1 plus 1 is 0. These will go away. These will literally just cancel and go to 0. And then minus the square root of 4, that becomes a minus 2. Let's change that color. There we go. A minus 2. And I get an answer simply of 1. So you can see how I get very different results. This, for advisement, this one right here, this is called a conjugate pair. We're going to take advantage of that because every time you multiply conjugate pairs like this, it gets rid of all the radicals, which we're going to learn is very fantastic to have when it comes to getting rid of radicals in complex fractions, or if you recognize a conjugate pair, you know that you can do a little bit less work. So to make sure we got that, they give us these 3 to practice. These all 3 are conjugate pairs. And so that means our final result should not have any radicals or square roots in it at all. Because if it does, then we didn't do the idea of a conjugate pair correctly. So I would recommend you pause the video and try these three on your own, and then unpause it and see how you did. Otherwise, I'm just going to go ahead and solve these now. So when I multiply this one times this one, I'm going to get the square root of 25, which is 25. I'm sorry, I said that wrong, which is 5. Square root of 25. So I'm going to write it out. This is one reason why I recommend writing it down. You get the square root of 25. This one times this one is negative square roots of 15. This one is positive square roots of 15. And this one is minus square root of 9. So what we notice is this becomes a 5. These will cancel out. And then you get a minus 3. And so your answer ends up being simply a 2. Right, we try again. 7 times 7 is 49. This one times this one is negative 7 radical 2. Notice how the 7 is not under a radical. This one times this one is positive 7 radical 2. And then this one times this one is negative square roots of 4. So we keep the 49. These cancel. Then I get minus 2. So our answer ends up being 47. One more to show on for exercise 6. This one times this one is the square root of 25. This one times this one is negative 2 square roots of 5. This one times this one is a positive 2 square roots of 5. And then this one is negative 4. So the square root of 25 is 5. These cancel out. And then minus 4. And so we get 1. So what we're going to do is for our very last example is we're going to put the practice of a conjugate pair to use. So in example number 3, we have this one we want to simplify, but we've got this radical in the denominator, and our goal is to get that radical out of the denominator. That's our ultimate goal. So what we'll do is we're going to duplicate this one to give us room to write. And so if I want to get rid of this, I need to multiply by something that's going to get rid of that radical. Right, so we'll put this one in parentheses, and we're going to multiply it by its conjugate pair. So minus 5, I'm going to put not a minus, but a plus 2 radical 3. Now remember, whatever you do to the bottom, you are going to have to do to the top. So I have to multiply by 5 plus 2 radical 3 in the numerator. Remember, our goal is to put this in simplest radical form. And for us, in this case, is to get that radical out of the denominator. Now, if you successfully wrote the conjugate pair, then in a moment, you're not going to have a radical in the denominator. So if we do 5 times 5, we're going to get 25. And we'll write it all out. 5 times this is going to be 10 radical 3. Negative 2 radical 3 times 5 is negative 10 radical 3. And now this one here is going to be negative 4 square root of 9. So the numerator, just so we multiply everything through, right? Maybe we'll make that line a little bit nicer. A nice line is always welcomed. So we do the distributive property here. 5 times radical 3 is 5 square root of 3. Remember, if it's outside the radical, you can't multiply it directly with what's inside the radical. And then here, square root of 3 times 2 radical 3, we're going to get plus 2 square roots of 9. And so our goal is to simplify this. So if we do that, right, let's look at the numerator first. Numerator is kind of nice. We can't do anything with this, so we leave it as 5 square roots of 3. But the square root of 9 is 3, so 3 times 2, and we get a 6. Now let's add a fraction bar. Now let's take a look at the denominator. And so this is a 25. These are going to cancel out. Square root of 3, or square root of 9 is 3. 3 times 4 is 12. So now we have a simple problem in the bottom of 25 minus 12. So now we just kind of clean up our answer, right? And you can leave it like this if you want, or you could rewrite it as 6 plus 5 radical 3. That way nothing's hanging out behind that radical. And then 25 minus 12 is 13. So that's one of the reasons why it's good to know what a conjugate pair is and how to take advantage of that conjugate pair in solving this information. All right, so if you have any questions, obviously you're going to want to inquire further with me and then move on to the problem set.